Hello, welcome back again to the lectures of offshore positioning of Geodesy and Geomatics Engineering in Institute Teknologi Bandung. Now we're going to continue our lectures in Module 10 about the gyroscope and accelerometers, continuing our previous lectures about the inertial navigation system. All right. We're going to continue our talk about the offshore positioning, typically with the gyroscope and accelerometers as our main sensors that normally be found in calculating or estimating the motions of our platform underwater, for example, for underwater robots, or also useful for the ship's motions that normally be found when you're using the IMU for estimating the motions of the ship so that you can correct the motions of the ship when you're doing the multi-beam survey, right? Yeah, we're going to begin with the gyroscope. As we know, the gyroscope measures the angular velocity, right? The common units of the measurement normally degrees per second on, or maybe radian per second can be also be used. So basically, how do we measure the angular accelerations or the rotation rates of the object, for example? The object is rotating about an axis, will have the accelerations, right, perpendicular to the velocity. So as we know from the previous lectures, if the aeroplane wants to fly from one point, from the North Pole, for example, to Jakarta, and because of the Coriolis effect, because the Earth is rotating, and the aeroplane will end up in Yogyakarta instead. It's because of the Coriolis effect. So we measure the angle based on the Coriolis effects, basically. It's the same as like here. If the car want to go from the center to the north, and instead is going to the north because of the Earth is rotating, for example, and we feel the rotations. The car feels the rotation, the car will go to the northwest instead, right? And we can measure basically the motions with 3-axis gyroscope. Means that it calculates the motion in 3 degrees of freedom, in X, Y, and Z axis. So one example of applications that normally be found for gyroscope measurement data is in the optical stabilizations, or common use is navigation control. And then when you're doing multi-beam survey, it can measure your pitch and roll, and then it can correct the motions of the ship's motions, and then it corrects the point cloud data of the multi-beam basically. So, but here we can see the optical stabilizations, and as you might also normally be found nowadays in the enhancements of technology of the camera and mobile phone, it can use the optical stabilizations, meaning that when you're taking a video and you're running with your camera, with your mobile phone, it will automatically doing the stabilizations by determining the motions of the mobile phones from the gyroscope measurement data, as we can see here. So this is the true rotations of the camera, for example, and then the smoothed out camera positions or camera motions from the gyroscope data. So basically the movement or the smoothing is based on the gyroscope measurement data, as we can see here, but of course it's as the percentage because it's the cropping image factor becoming more larger than the raw image data input. Yeah, okay. If we're talking about the gyroscope, of course, we'll have to rely on the gyroscope model to be able to get the as correct or close to true values of our estimated angles at the end. So basically this is the angle that we want to, the rotation rate that we want to aim, that we're looking for. And then this is the true angular velocity. And of course we have these two errors every time we're doing the measurement with gyroscope, which is the bias and the Gaussian noise. And the bias is temperature dependent. It may change over time, can be approximated as constant. And then we can do the error modeling by using the Taylor expansions because it's useful to estimate the error even though the error is slight. So we can do it with the Taylor expansions, for example, here. And then this is, as we said, this is what we wanted. This is the angle of at the current times. And then what we have is the angle as at the last time step. For example, the angle at the last time step was 0 because it wasn't moving. And then it starts to move so that we have the angular velocity from the gyroscope measurements after the mobile phone is moved, for example, from 0 angle to that the time 1 now it becomes, for example, 10 degrees. But of course it has the error, the approximation error. And basically the gyro measurement, we can derive the angles from the gyro measurement by integrating the angular velocity and then or vice versa, deriving the angle that we're looking for or that we have into the angular velocity as we said here, as we can see here. But to be noted, if you're going to work with our data, the units is very important to note. So either we're using the radian per seconds or degree per seconds. So for example, for estimating the orientation from the gyroscope or integration of angular velocity, for example, we have to integrate our angular velocity to get the orientations, right? As we can see from the gyroscope model. And the gyroscope data basically provides the angular velocity as we can see here. And we can integrate that to find the angle at the time t. And this integration is basically the integration process basically give the relative orientation change over the time. For example, we have the starting angle 0 degree because the gyroscope was stayed still. And then the gyroscope measures a movement about 1 degree per second. And after 10 seconds, of course, the estimated angle is about 10 degrees. But of course, we have to add the error later on, right? So the error has to be considered, which is the bias and the noise here. So, right. The things that we have to consider if we're working with the gyroscope, of course, if it's a linear movement, meaning that the gyroscope is attached to the, for example, mobile phone, and it goes, for example, this is X and Y, X, and the gyroscope is going to that positions, and it goes to with the linear movement, so it only goes one direction of axis. And it might be okay if we are not considering the noise and the bias inside our measurement, if it's only the linear movement. But still, this is not the ideal case. So this is rarely happening if especially if you're working in underwater or in offshore positionings where the movement is really more or less influenced by the water properties or the current state of the water, for example, because of the wave, because of the current, or because of the water properties itself, because of the salinity differences, pressure differences, and so on. So it might influence the movement of the vehicle so that the vehicle is not moving in a straight line anymore. Instead of it's moving in the 3 degrees of freedoms in each three axes, X, Y, and Z, at every time. Of course, in that case, we're going to forget about that first. Here in the linear movement, if we introduce the bias, then we might see the discrepancies between the ground truth, which is the blue line, and the estimated gyro data measurement. You can see here, the gyro is more or less more not stable with the bias introduced to the measurement data. And if bias and if bias and noise are present, of course the drift will be increased over time. The drift will be larger and larger and larger over time. So it might be really tricky if you're going to go in one straight line. So for example, we design the AUV to be typed in and collect the data from one port to another port. For example, here, this is the port 0, this is the port 1, port I, and then we set the mission plan to go from one port and then collect or detecting the underwater pipe, for example. Here, it sends the underwater pipe, it has to follow the pipe, but because of the drift over the times, it might no longer following the pipe, so it might go that way instead of going. So the initial plan was to collect the data after the AUV is appearing in the port I, for example, but instead of port I, the AUV may be appearing in the somewhere in the middle of oceans, for example, in the position of G. Position of J. So of course the drift is preserved over time, which is a bit tricky if we are not considering the drift and because of the bias and the noise, basically. And if we're talking about the case in offshore positioning, so of course the motions will be non-linear, so the drift will be even more preserved over time, even though there is no bias and noise in our measurement data. And with the presence of bias and noise, of course, the drift will be even larger over time. So you can see here, it gets larger and larger over time, and the measurements are not so seamless anymore. Right. So that was the case and how we get the data, basically. So there are different kind of gyroscope that we can use or that we can attach to our platform or to underwater bodies, to underwater platform. The most common gyroscope is the spinning mass gyroscope. So it has the base and it has gimbal and it has 3 degree of freedom of movement by frame, spinning axis, and rotor. For example, a simple spinning mass gyro consists of a rotating wheel or ball. For example, here. So this is the initial axis. This is like the example if you're holding the rotating wheel of the bike, for example, or bicycles. And then if we are holding the rotating wheel like this, or in the initial axis in here, perpendicular to our base, for example, our base axis, the gyro will not be moving. But if we start to tilt the wheel towards outer area of the axis, of course, the gyro will be moving in clockwise directions or counterclockwise directions if you're tilting that in a different way, right? And the other and the other most famous gyroscope that already been implemented also in our mobile phone is the micro electromechanical system, or the MEMS. The MEMS is so tiny, so that because it's so tiny, it can be placed into our mobile phone. So it's so easy and so convenient, and it also can be embedded into the micro computer, so that the microcomputer can be attached with the gyro and then be attached later on with our platform underwater, for example, so that we can later on reduce the space needed for having the sensor that requires to detect the motions of the ships. So for example, here we have the frame of the MEMS, and the frame is basically has the P, which is the mass, and it's connected with the coil, and when it detects the cordless effects, and it induce the secondary vibration along the axis, and then the mass try to balance basically the frames by moving in another directions. And this movement of masses then be translated, or this rotation causes a change in the output of the differential uh, measurement of capacitance, and then as the rate of rotation increase, so as long as it's rotated, so the displacement of the masses also increases, and then it's producing the signal of the Coriolis force based on the Coriolis force, and translates as rotations. But still, it might be not that accurate, because it sends the rotations from the Coriolis effect, right? So if it's only small rotation, the mice may be not moving. So because the mass is stand still, it doesn't detect any rotation, even though we try to tilt our gyroscope a little bit. So that we have the more accurate gyroscope, which is the fiber optic gyroscopes, or FOG. This is more accurate because it based on the pulse of laser, for example. It goes, we have two pulses of lasers, the red and blue, for example, here. And basically, it always going in the known lengths of motions. But if it's tilted a little bit, the red one will go a little bit slightly longer than the blue one, for example, or vice versa. And then by doing so, we can always detect, even though there is slight motions, because it's based on the Sagnac effects, as we can see here, to determine basically the rotational rates of the unit. All right. And then we go to the accelerometers. So basically, this is the example. If we are assuming our body is accelerometers, it determines the physical accelerations of an object due to the inertial forces. And it measures the linear accelerations with meter per square quadrat. This accelerometers basically doesn't measure the change of speed, but the applied force to the body. So it's basically sense how much the mass presses on the sensor when the force applies. For example, here, when the ship start to move, our body try to uh, be pulled back, right, to the back of the ship. So like when we are accelerating with our car, we press the gas, and then our body stays still, but our body will be pulled back to our chair, right? Because this is the assumptions of our body becoming accelerometer, so it senses how much the mass presses on the sensor when the force applies. And one of the examples is for the behavior analysis. So when we attach the accelerometer, for example, on top of the body of the turtle, and it will try to sense the movement of the turtle, basically, and then it correlates the movements of the turtle with the behavior of the turtle, what does he do at that kind of behavior, and then with the movement of the accelerometer, for example. For example, if it's going upward, up, downward, or stay still, or can be correlated like when looking for food around the rocks, giving impressions of grazing, and etc., etc. And yeah, this is one of the example which is interesting for us to see because it can be correlated with the marine behavior under the water. Or the most simplest applications is for determining the positions of the underwater objects, right, on the underwater platform. So the accelerometers model, we have here our accelerations in time t at certain times, and then we have the gravity vector based on the gravity vector downward. This is 9.81 meter per second quadrat, and then if we apply another external force, that will be having the measurement that measured by the accelerometers. So as we note here, the gravity vector is always there, always be sense. And then another thing that measures by the accelerometers is the external forces. If we apply the force that cause the movement of the, for example, mobile phone. But of course, there are noise or error that has to be considered. So without motions, we only have the gravity vector, which is pointing downwards with magnitude of 9.8 meter per second quadrats. And with motions, of course, the combine of both vectoral forces and gravity vectors, right? And then we're going to talk about the types of the accelerometers. For example, the first one is the mechanical one. And this kind of accelerometers basically has a mass that's attached to the spring and a damper. Then the spring is suspended inside the outer casings, and when it accelerates, when we try to accelerate, and this accelerometer is attached to our body, and then the mass will stay behind, and the spring stretch. So the spring stretch with a force in tandem with acceleration, and then the stretch kind of things is then translated into the accelerations that measure to our data. Yeah, so this distance of the spring stretch, yeah, the longer the spring stretch, or the narrower the spring stretch is used to measure the force and the acceleration that applied in many ways. So, for example, the seismometers used to measure the earthquakes because also the kind of vibrations and similar way in this manner depends on heavy masses are attached to the spring to register the earthquake force. So this earthquake force is external force, and because of that earthquake force, the spring is stretch, translate to vibrations. And then piezoelectric accelerometers are usually used also for vibration and shock measurements, work somehow also the same. It has the base and it has the piezoelectric materials like transducer, but the thing is with transducer that you apply the electrical input, and this electric input is translated into an acoustic by using the piezoelectric mechanical. So this electrical value, the electrical input will then vibrate your transducer, and then this transducer will producing the acoustic signal. And this one is vice versa. For example, acoustic signal is received by the piezoelectric mechanical, and then the piezoelectric mechanical starts to vibrates, and then it translates into an electronical values or somehow similar. And then we also have also similar way with the piezo-resistive accelerometers and some time or it's also suited for vehicle crash testing and it's far less sensitive than piezoelectric accelerometers. So for example, we have the mass that attached to the piezo resistor here. So the piezo resistor, when an external force applied, the piezo resistor will trigger and then the mass will try to uh, be stretched by means of the stretching of the piezo resistor, basically. And it translates again the force that's experienced by these accelerometers becoming the accelerations. And then also similar with the gyroscope, we also have accelerometers in our mobile phone, right? Which is the microelectromechanical system, the MEMS, that is found in the capacitive accelerometers. So for example, here we have simple MEMS accelerometer scheme. So we can see in the pictures and the anchor, basically the anchor A hold the proof of mass in B. So the mass can be probably be stored in here and it has the center sections, several center sections, for example. And then yeah, when the applied force experienced by these accelerometers, the electrodes then will receive the movement of the center masses, right? Uh, and then the movement of the center masses based on the speed, based on the time stamps between one point to another point, will then translate into the accelerometer's value. When the accelerometer is at rest, or fixed as traveling at a fixed velocity or zero acceleration, the fingers are in the center position. So in the center position, so it doesn't have any measurement values, but when it's experiencing the applied force, the external force, either that way or that way. So these electrodes will have then the input of the string mass, yeah, of the center mass. All right, we have different kind of accelerometers and the gyroscope. Each of them has disadvantages and advantages. Of course, the MEMS is most common way to use to be used, but of course, it has more or less more noises because it's based on the microelectronical component, but sometimes the microelectronical component doesn't really detect even, for example, the slight movement of the sensor. So it might be also tricky, and also the noise can be probably bigger than the other type of sensors. And we have the model of gyroscope and we have the model of accelerometers. And basically, how do we integrate the gyroscope and accelerometer sensors, right? The challenge is you want to estimate the orientations of both by using both sensors. The challenge is in gyroscope is accurate over short times, but drift over time due to the integrations. And the accelerometers provide absolute orientations, but noisy and sensitive to linear motions. Yeah. And then the solutions is to combine both sensors to stabilize the orientation estimations. Why we combine them actually? Because the accelerometers alone can give rough estimate of orientations by sensing gravity, but they are prone to noise and drift over times, as same as gyroscope provide better short-term orientation change or rotation rates, but suffer from drift over time. And by combining both, we can filter out the weakness of each sensor and create a more stable and accurate orientation estimations. And yeah, what we have to consider first is the relationship between the sensor frames, right? So the rotations between gyroscope frames to the acceleration frames. Here, you can see here. So we have the body-to-body transformations and data time synchronization, because it wouldn't make sense if we are recording the data with different timestamps, and we cannot integrate our data basically if we are doing that. So just let's go to the example of the sensor fusion into the orientations. The problem is the drag angle into the space. So for example, the IMU stands still like this, and then it tilted. We have, for example, one gyroscope and two axis accelerometer X in X and Y directions of axis. And we want to know the rotations theta based on the z-axis. So the z-axis is pointing downwards there, for example, right? So in order to take the movement of rotations in z-axis, as we know, we have the gyro model with the expansion from the Taylor series. So basically we have the timestamps delta t, and we want to look for the angle at time t based off the previous angle of time -1, for example, 0. And then we will have the measurement of angular rotation rates, which is the omega. And then by doing the integrations, we'll be having later on the angle, right? But of course, to be noted is the accumulated drift. And that was the gyroscope. And then we can also derive the angle from accelerometers. So basically, the accelerometer measure the movements of the acceleration vector. So you can see here the blue line, and it based on the accelerometer y-axis and the x-axis. And basically we can measure the angles from the so basically we can measure the angle of theta by using the arctangent of acceleration vector in x-axis divided by the acceleration vector in y-axis. But of course, we have to consider the noise that accumulated over time. And then we have here the 2D orientation, how we combine them basically. And we combine the gyro and accelerometer measurements by removing the drift from gyro via high pass filter. So what does it mean? And removing the noise from accelerometer via low pass filter. What does it mean? So for example, this is the example of using the filtering technique, which is the complementary filter. There are also different kind of filtering techniques. For example, Kalman filter or Gaussian filter or any Bayesian filter or any other different kind of filtering techniques. For example, here we're talking about a complementary filter, and we have the filter coefficient alpha here. Normally it lies between 0 to 1, and the common value is using 0.98 because it based on the gravitational factor that pointing downwards, for example. And the high pass filter here, meaning that we are putting more weights in our gyroscope measurement data. So for example, here the alpha we're putting directly 0.98 into our filter coefficient, meaning that at the end, it has more weight, because here, as we can see in our accelerometers, so this is the gyroscope, right? And this is the accelerometers, right? And here, as we can see here, the coefficients is subtract by 1, meaning that we'll have, instead of 0.98, we'll have 0.02. So meaning that we will have less weight in accelerometers, so we'll be having low pass filter in comparison with the gyroscope that has more weight, which is the high pass filter. And then by doing so, we can minimize the drift and the noise. But of course, in other different kind of case, other filtering technique might be suitable because this complementary filter may not be really significant of minimalizing the drift and the noise of our measurement data. So for example, here we want to have the fit angle calculated from the gyro and accelerometer. So basically it has to be fit to each other. The gyroscope measure the angle that integrated from the rotational rate. As you can see here, there are slight movement in our measurement data, and the accelerometers measure the angle from the acceleration vector, right? And how to properly or fuse both and by using complementary filter or, for example, Calwan or etc. And then if we go back again to a previous lecture, we were talking about the Euler angle, and this Euler angle is also useful if you are going to talk about the 3D motions that measured by our sensor, right? For example, the pitch and roll angle computations from accelerometers, assuming that no external forces, only the gravity. So we'll be having rotation in X, Y, and Z. So as we can see here, the sensor is a bit tilt or pitch tilt, for example, and then it producing the angle theta to our base axis. And yeah, we have the G pointing downwards, and then we'll have this is the accelerometer vector Z, accelerometer vector X, and also accelerometer vector Y in the other directions, and also the G pointing downwards. Then we will have the correlations. So we will have the at the end the Euler angle computations, the relationships between before I was tilted and after it's tilted with the Euler angles, right? So we have this, for example, 1, 2, and 3. And we have to note that the formulations of this rotations matrix is very important. If you are putting 3, 1, 2, for example, we are calculating first we're putting first the rotation matrix of Z, and then X and Y, then we'll be having different kind of value at the end here. But here we have the, for a simple case, we'll have the 1, 2, 3, and then at the end we'll be having, after we putting a filter, we're calculating all the Euler angles together, we'll be having this matrix. So yeah, all right. Then in the 3D motions, of course, with assumption that there is no external forces applied to our measurement data, only the gravity, and we'll be having the normalized acceleration vector here, which is if it's we'll be having, of course, the relationship between the Euler angles. We'll be having this matrix, and basically it's connected with the normalized acceleration vector. And when the accelerometer is not accelerating due to any other movement or force, like lateral force or rotational force, or if there are other external forces acting on it, such as forward push or tilt in a moving vehicle, this could introduce errors in the computed pitch roll angles. And the normalized acceleration vectors is basically computed as follows, as this one. So the accelerations basically represents the raw accelerometer reading along the X, Y, and Z axis. and the magnitude of the accelerations, which is the normalized accelerations, or the magnitude or norm of the acceleration vector, making the acceleration or the unit vector magnitude of 1, for example, representing the directions of the accelerations without considering its strength. And yeah, well, expected gravity components based on the orientation or pitch and roll. And then we'll be having the normalized acceleration vector in terms of pitch, for example, and roll, for example, yeah. And for roll, for example, here, we'll be assuming pitch is really, really small or nearly horizontal. We'll be having acceleration vector of y divided by z. This equation allows us to calculate the roll angle directly from the normalized accelerometers measurement data or readings. And then the pitch one formula is this one. Basically, the formula pitch is when roll is also considered, right? The formula basically calculates the pitch angle based on all three accelerometers components, where accelerometers in x, y, and z are normalized in magnitude in accelerometers reading. So basically, these equations provide a way to compute pitch and roll angles from accelerometers readings under the assumptions that only gravity is acting on the accelerometer. So the device is not accelerating in any directions, and the pitch and roll are determined based on the orientation of the accelerometers with respect to the gravity. If external forces act on the accelerometers, they will affect these measurements again, of course, and the computed angles may no longer be accurate for determining the orientation relative to gravitational field. All right, and you can also see the example of using the complementary filter in this YouTube video, but it's only for a short. You can see here, yeah, this is the demonstrations of measuring the tilt of using accelerometer. For example, this is our sensor, the IMU. It has the gyroscope and accelerometers inside it. So you can see here our data, it's showing tilt angle. As long as it's smooth. And it applies the complementary filter from the noisy accelerometers data. And yeah, instead of the white one, I think we produce the green one, or vice versa. Yeah, it says that we can see the noisier output from our measurement data. And then by using the complementary filter, it can filter out the noisy data. So with no complementary filter later on, we can match both measurement together, fuse all of them together. It produces less bias and noise. You can see here, yeah, it gets better and better. So this is one example of using the complementary filter. But of course, there are also examples of using other kind of filtering techniques. All right, I think that's all. I hope we can give you brief informations of how you can use the gyroscope and accelerometers all together, and basically what type of gyroscope that can be used to our underwater robotics platform in offshore positioning techniques, for example, and what kind of models that apply to our gyroscope and accelerometer measurement data. And yeah, we're going to talk about how we do the sensor fusions and also other integrations of the gyroscope and accelerometers later on in other lectures. And I think that's it. Thank you for watching. Hope you enjoyed lectures. I'm Fikri Muhammad. I hope to see you in the next lectures. Bye bye.